Now we want to start our discussion of functional groups, what's on the hydrocarbons, talking about alcohols and ethers. So an alcohol is a compound that contains a hydroxyl group bonded to a carbon atom. So a hydroxyl group is an oxygen bonded to a hydrogen. So in this representation, red is oxygen, the black molecule is carbon, and the white molecules are hydrogen. You can also see it drawn over here in the Lewis structure. So whenever we have an O bonded to an H, where the other side of the O is a carbon, that is called a hydroxyl group. That is the functional group. Molecules that contain a functional group, that contain a hydroxyl group, are then called alcohols. So the whole molecule is classified based off of the functional groups that are present in the molecule. And so, we can see there's kind of this language. The name of the functional group is hydroxyl, and the name of the class of the molecule is alcohol. And the ending for alcohols is ol, or ol. So any molecule whose name ends in ol is an alcohol. Just like alkane, where the word alkane ended in ane. So the molecules all end in ane. Alcohols end in ol. So methanol is an alcohol. And there's a lot of different varieties for alcohols. So you can just get more and more carbon atoms. Methanol was one. Ethanol, pentanol, 1, 2, 3, 4, 5, 6, octanol. You can keep getting bigger and bigger, where you basically just have long hydrocarbon chains with an OH added on. You can also have more than one hydroxyl group on there. So you could have something diol, means two alcohols, two ox, and so you can get one hydroxyl group right there and one hydroxyl group right there. You can also get even bigger carbohydrates. This thing's got a bunch of hydroxyl groups on there, a bunch of decoration of a bunch of oxygens in that molecule. So ethers are then the other type of organic molecule that contains single bonded oxygens. But in this case, the oxygen atom is bonded to two carbon atoms. So you can think in an ether, the oxygen is like part of the structure of the molecule, not hanging off the side. And so in this case, there's no group name because an ether oxygen is just one atom. This one atom is the functional group. It is the ether oxygen, so you don't have any sort of fancy names. There's no suffix when you're ending ethers. There's the word ether will show up in the name. So for example, dimethyl ether is the smallest ether. So you can generally tell ethers pretty well because the word ether shows up in the name. In terms of the smallest, you do have to have two carbon atoms in an ether because it has to be oxygen bonded to one, bonded to two carbon atoms. So you do have to have at least the two in there. When we think about ethers, the oxygen is less of kind of a decoration like it is in the case of an alcohol, and it's generally more structural. They can't hang off the side because you have to have carbon atoms on both bonds of the oxygen. So something like this, where it's in the middle or linking together alkane chains. The ether oxygen can also be a part of a ring, right? Where it's just kind of part of the ring holding everything together. There's no hydrogens attached to it. Instead, it has the lone pairs completing its octet, still part of the ring. We can also see one shows up in the same molecule we looked at for the alcohols. Overall, this molecule is a carbohydrate. This is starting to get at kind of more complicated. This is a biochemistry application where you can see there's different types of functional groups in this molecule. In this case, hydroxyls, right, the OHs, and the ether oxygen. And that makes it a particular type of molecule called a carbohydrate. So this is erythromycin. We looked at it at the end of our alkene video, talking about we have the hydrocarbon backbone, and then we're going to decorate it with some functional groups. So let's diagnose what functional groups are in this molecule. I want to know how many hydroxyl groups are there in a molecule of erythromycin, and how many ether oxygens are there in a molecule of erythromycin. All right, so first we want to look for hydroxyl groups. So hydroxyl groups, this is the name of a type of functional group. And so when we're looking for hydroxyls, we're just looking for OH. So anywhere that we see OH in the molecule is going to be a hydroxyl group. There are multiple hydroxyl groups in here. We want to note not all oxygens are hydroxyl groups, only when it's attached to OH. So we got 1, 2, 3, 4, 5. Looks like all of them. These H's, that's just H's that are being explicitly shown in the molecule. Not they're close to hydrogens, but we want to be careful. It does need to be bonded to. It would be written right next to it, similar to how we've seen in condensed formulas. So there are 5 hydroxyl groups in the molecule. Well, now what about ether oxygens? So ether oxygens are oxygens that are bonded to 2 different carbon atoms. So we want to be careful. What we're looking for is a pattern where it'd be line, O, line. It's going to have at least 2 lines sticking out of it. So something like this. Something like this. That's a dashed line. That just tells you it's the direction this molecule, its 3-dimensional shape is being shown. Here we've got another one. Wedges are still just bonds. Oh, right here. We can see here I have an oxygen that's double bonded to 1 carbon. That is not an ether. That does have a name, and we'll come to that soon. But we want to be mindful. Ether oxygens, where it's 1 oxygen that is single bonded to 2 different carbon atoms. Not the same, not a double bond. So those don't count. So we got to count these up now. 1, 2, 3, 4, 5, 6. So there are 6 ether oxygens. So the common link between alcohols and ethers is that they both contain oxygens. And we know that oxygens impart polarity into molecules. And uniquely, especially when we're dealing with, say, an alcohol, the OH can start to form hydrogen bonds. So that really increases, say, the intermolecular forces between different alcohols. Even though the single oxygen of an ether molecule can't form hydrogen bonds on its own, it can receive the hydrogen bond of, say, a water molecule. And what that starts to imply is that alcohols and ethers have more water solubility than their parent hydrocarbons. So alcohols tend to be quite soluble in water, whereas ethers tend to not have as much because, again, they're not really kind of a one-way participation in the hydrogen bond. And so we do start to see this is when we start to add in these functional groups, we can really start to play with the physical properties of a molecule. Now, as alcohols get bigger, as the hydrocarbon portion of the molecule starts to get bigger and bigger, that starts to become more important when we're talking about, say, solubility. So if you have, say, this is 1, 2, 3, 4 carbon atoms, and then the OH attached over here, yes, this part of the molecule is polar and can form all these hydrogen bonds and would imply there's some solubility in water. These carbon atoms really don't want to dissolve in water, and water doesn't want to have that floating around in it. And so when we start to look at the solubility of alcohols, small alcohols, say 1, 2, 3 carbon atoms, very, very soluble in water. But as you start to get bigger and 4, 5, 6, 7, 8, 9, 10, or 10, sorry, we skipped 9 there. Eventually it's insoluble in water. It's decreasing more and more, right? Less and less soluble until eventually it's not soluble at all. And so when we're starting to talk about the solubility of an organic molecule in water, we need to consider both sides of the molecule, the nonpolar hydrocarbon component and the polar oxygen containing component. So inclusion of a functional group into a molecule can modulate or change the properties of the molecule, but it won't overall determine the properties of the molecule. So OHs, oxygens, tend to increase the solubility of compounds in water, but they're not going to overwhelm a lot of hydrocarbons. So for example, cholesterol, C27H46 O. There's this single hydroxyl group hanging out over here in a cholesterol molecule. There are 27 carbon atoms, though. Overall, this is a very, very nonpolar molecule with just this tiny little bit of polarity. This molecule is not soluble in water because, yeah, there's a hydroxyl group in there, but it's a small component of the overall molecule. It's not going to overwhelm the properties of the entire rest of the molecule. There is some sort of balance between these, and in this case, the nonpolar hydrocarbons, which is way more, overcomes the very strong polarity of a small portion of the molecule. Sucrose, on the other hand, which would be like sugar, 12 carbons, 11 oxygens. You will note there is basically one oxygen for every carbon atom. They show up as both, we have hydroxyl groups over here, hydroxyl groups, kind of decorating the outside. We also have plenty of ether oxygens in the structure of the molecule. And that overall allows for high levels of polarity. Yes, there are still plenty of hydrocarbons, right? This sort of kind of ring here is all carbon-based, but there's a lot of oxygens that overcome that there's kind of this balance. In this case, in the case of sucrose, you're tipping the scale towards polarity and towards solubility in water, whereas the case of cholesterol, it is squarely tipped towards nonpolar. That is very nonpolar, very not soluble in water. In addition to the physical properties, alcohols are also going to have certain chemical properties. And the primary type of reaction that alcohols can do, or one of the big types of reactions that alcohols can do, is oxidation and reduction. And so oxidation and reduction in the context of an organic compound really is technically still transfer of electrons. Oxidation is loss, reduction is gain. But because organic molecules follow consistent patterns of reactivity with only a handful of atom types, we can also view oxidation as the addition of oxygen, and reduction is the loss of oxygen. So basically, literally how many oxygen atoms in a molecule, how many bonds are to oxygen. We can also view it as oxidation is the loss of hydrogen and reduction is the gain of hydrogen. And so those sorts of kind of views, or kind of this sort of different kind of way to look at oxidation reduction, it still changes in oxidation number. It just has to do with changes in oxidation number due to adding in oxygens or removing hydrogens or vice versa. And so when you're oxidizing an alcohol, functionally what happens is the carbon-oxygen single bond becomes a carbon-oxygen double bond. So that is the sign of what we're looking for oxidation of alcohols. In the lab, when we're doing this, we use some pretty gnarly reactants, potassium dichromate with sulfuric acid. This is pretty unpleasant conditions. It's very reactive. Alcohols aren't super reactive. They don't necessarily really want to oxidize, but you can make it happen by kind of using a sledgehammer here to do that oxidation. This is also a really common process biologically. This is how organisms process alcohols. They oxidize them to be able to metabolize them and treat them, or that's how they metabolize them. So when an alcohol molecule undergoes oxidation, it really happens in two steps. You can see that first, we take this carbon-oxygen, it's a single bond in the alcohol, and then it becomes a double bond. So that's the first step in the oxidation. And then the second step is basically this bond down at the bottom is carbon-hydrogen, and basically an oxygen gets inserted into there. So a second oxygen is put in. So oxidation can be thought of as basically our making more carbon-oxygen double bonds. So in the first step, basically a single bond becomes a double bond, and then after that, we just make a new bond to carbon-oxygen. So when we're in the lab, if we're working and we have an alcohol and we try to oxidize it, we're using such strong reactants, such strong conditions that we just blow past this and get all the way to the full oxidation. We are never really gonna, it's very, very difficult to get this partial oxidation product in the lab. Now, biologically, organisms do these steps one at a time. There's a lot of very strict control on the kinetics of each process that an organism can produce just the first step and produce that product with just the double bond and without the second oxygen atom added in. So there's a lot more control in that context. Now, when that's kind of the idea of how we can do oxidation or what it could look like, but when there's other carbon atoms kind of in the area around the hydroxyl group, it actually affects whether or not oxidation can occur and how far it can occur. So here we can see in this top molecule, this is the carbon atom that's attached to the hydroxyl, and it's bonded to 2 other carbon atoms. What that actually means is that you can only do the first step of the oxidation where you create the double bond. There's no second step where an oxygen atom gets inserted in because there's no hydrogen atoms that are attached to this carbon atom that you can have an oxygen insert into. Instead, it's stuck at just being the double bond. In the case here of, say, this molecule on the bottom, where we have, here is my carbon atom, and it's bonded to 1, 2, 3 other carbon atoms, this cannot be oxidized at all. It doesn't matter what you're using in here, because in the process of oxidation, this bond right here, this carbon-oxygen bond, is going to be turned into a double bond, right? So that would increase the bonding on that carbon atom, but it's already bonded to 3 other carbon atoms. You're not going to break any of those. You're removing hydrogen atoms in order to facilitate oxidation, not breaking carbon bonds. So while hydroxyl groups are in general susceptible to oxidation reactions, not always. It depends on the local context, kind of the local environment of the molecule where that hydroxyl group is located. And the more carbon atoms that are around, the more resistant that hydroxyl group is to being oxidized. So ethers are extremely non-reactive. So alcohols, some of them not very reactive. All ether oxygens very non-reactive. They cannot be oxidized. They are not susceptible to acid or base reactions. And so again, just like hydrocarbons, ethers tend to be used as solvents. They're really, a lot of them are liquids at room temperature. They're really good at being solvents. These two right here, diethyl ether and tetrahydrofuran, that are shown down at the bottom, are very, very common organic solvents. Even though there is an oxygen in there, still these molecules are still relatively nonpolar. There's just so much carbon in there. They're pretty nonpolar, and they're really used quite frequently as solvents. They're still flammable, just like alkanes were, but they have a lot of utility to dissolve a lot of things. So with our newfound knowledge of hydroxyl groups and ether oxygens, we can return to erythromycin. So erythromycin, we said that the hydrocarbons form the backbone, and the properties of the molecule are going to come based on those functional groups. So there's hydroxyls and there's a lot of ether oxygens. So all of those oxygens make this molecule more polar and make this molecule soluble in water. The hydrocarbon backbone was not going to be soluble in water. There are a lot of carbon or oxygen atoms in this molecule that make this molecule polar enough to dissolve in water, which is really important because if we're going to use this thing as an antibiotic, it needs to dissolve in the water that makes up a human's body, right? There's a lot of water in a body, and so the molecule, in order to be biologically active, it needs to be able to dissolve in water. So there's a lot of oxygens. But on top of that, you'll note a lot of them are ether oxygens, which are not reactive. And then of the hydroxyl groups that are in there, a lot of them are bonded to carbons that are bonded to a lot of other carbon atoms. That means they're not really susceptible to oxidation, which is kind of one of the main processes that goes on in, say, in like digestion in your stomach. And so this erythromycin molecule, it'll be soluble in water and it'll be resilient to, say, the reactive kind of degradation that could happen in an organism. So that's why it's useful as an antibiotic. So we can start to parse out some of the, make predictions about the properties of this molecule based on the functional groups that are in it. Okay, first video down. No questions on participation 12.5 yet, but don't worry, plenty more videos to go. Week 15 homework due this Saturday. Don't forget it. The last homework of the semester tends to be the one that's most often not done. Depending on when you're watching this lab technique presentation, your video, if you haven't turned it in, is due
Thursday the 4th by email. And then our final exam will be next week, Wednesday, the 10th at 11 a.m. in room 230. Before we can do that, we got to finish this set of videos. I will see you in the next one.